Dear students, good morning. Today we are going to discuss the topic on Lagrange's equation of motion. We derive the Lagrange's equation of motion using holonomic constraints. So now Lagrange used D'Alembert's principle to derive the equation of the motion. We know that the D'Alembert's principle is summation I equal to capital 1 to n Fi minus Pi dot delta Ri equal to 0. Here Fi represents the external force and Pi is the generalized momentum. Delta Ri is the virtual displacement. Here the virtual displacement delta Ri are not independent. So now we consider a system with n particles at r1 vector, r2 vector, rn vector and having k equations of holonomic constraints. Now the system will have small n equal to 3n minus k generalized coordinates. Say these coordinates are q1, q2, etc. q small n. Now we form the transformation equation from r variables to q variables using this equation. Ri vector equal to Ri vector of q1, q2, etc. qn comma t. Name this equation as 2. Now here the virtual displacements does not involve time. So therefore from the equation 2 we get delta Ri equal to dou Ri by dou q1 into delta q1 plus dou Ri by dou q2 into delta q2 plus etc. dou Ri by dou qn into delta qn. While differentiating dou Ri by dou t will be 0, so we omit it. And we write the summation form delta Ri equal to summation j equal to 1 to small n dou Ri by dou qj into delta qj. Name this equation as 3. Here delta qj's are virtual displacements of the generalized coordinates. So from which we can find the value of differentiate with respect to t. We get dou Ri dot equal to dri by dt equal to, so this can be written dou Ri by dou q1 into q1 dot plus dou Ri by dou q2 into q2 dot plus etc. dou Ri by dou qn into qn dot plus dou Ri by dou t. This is obtained from the equation 2. Now Ri dot can be written in the summation form summation j dou Ri by dou qj into qj dot plus dou Ri by dou t. Name this equation as 4. Now you differentiate Ri dot partially with respect to qj dot, we get dou Ri dot by dou qj dot equal to, so we are differentiating only qj term, so other terms are become constant, they become 0. So therefore you will get only one term dou Ri by dou qj into when qj dot is partially differentiated with respect to qj dot, it will become 1. Now we find the value of summation I fi into delta Ri equal to, so summation fi into, we replace from the equation 3 we can replace delta Ri by summation j dou Ri by dou qj into delta qj. So now we go back to equation 3 here. Delta Ri equal to summation j equal to 1 to n dou Ri by dou qj into delta qj. So now taken we take on the summation j outside, j equal to 1 to n, we take on the summation I into fi into dou Ri by dou qj into delta qj. So now here the term inside the bracket is summation I fi into dou Ri by dou qj is, we write it as capital Qj. So therefore summation fi into delta Ri equal to summation j equal to 1 to n capital Qj into delta Qj. Name, we give name this equation as 6. Here capital Qj equal to summation I fi into dou Ri by dou qj is called the jth component of the generalized force. Now next we find the inertial force term summation I pi dot into delta Ri equal to, so now mi into Ri double dot, the value of p equal to mv, mass into velocity, pi dot equal to m into Ri dot, pi dot equal to mi into Ri double dot. So now here pi dot is replaced by mi into ri double dot into delta ri, and again from the equation 3 we substitute the value of delta ri as summation j dou ri by dou qj into delta qj. Now in this term add and subtract the term summation I mi into ri dot into d by dt of dou ri by dou qj into delta qj. We take summation j outside. Within the previous term mi into ri dot into dou ri by dou qj delta qj. With this term we add and subtract the above term. So therefore we get summation j we have taken outside. In the three terms delta qj is common. You take delta qj outside, and finally we get summation j into summation mi into ri double dot dou ri by dou qj into delta qj. Delta qj we have taken outside, and from the second term you write remaining terms are summation mi into ri dot into d by dt of dou ri by dou qj minus mi into ri dot into d by dt of dou ri by dou qj. Now these two terms is the differentiation of d by dt of mi into ri dot into dou ri by dou qj. So if you differentiate mi ri dot into dou ri by dou qj with respect to time t, you will get the above term. You take mi into when ri dot is differentiated you get ri double dot. You take mi into dou ri by dou qj as it is. And similarly, and next we keep mi ri dot as it is, and we are differentiating dou ri by dou qj with respect to d by dt. So therefore these two terms are the expansion of the differentiation of mi into ri dot into dou ri by dou qj. So the remaining term we take as it is. Name this equation as 7. Next we separately find the value of the first term in the equation 7, that is namely summation I into d by dt of mi into ri dot into dou ri by dou qj. This can be written in the form mi ri dot dou ri by dou qj. We know that it is equal to dou ri dot by dou qj dot. This is obtained from equation 5. So we substitute here, and we write ri dot is nothing but a vi. So ri dot is replaced by vi, mi into vi into ri dot again dou vi by dou qj dot. So from this term we take d by dt of dou by dou qj dot we are taking outside. So we get summation I into mi vi can be written as half into mi vi square, while a differentiation term you are getting. So here half into mi into vi square represents the total kinetic energy of the system. So therefore it represents d by dt of dou by dou qj dot of dt. So finally we get d by dt of dou t by dou qj dot. This is the answer of summation I d by dt of mi into ri dot into dou ri by dou qj, where t is the total energy of the system. Now next we change the order of the differentiation in the second term of the equation 7. Here the second term of the equation 7 is summation mi into ri dot into d by dt of dou ri by dou qj. In this term we change the order of the integration. So therefore summation mi into ri dot into d by dt of dou ri by dou qj is written as summation I mi into ri dot into so now ri dot is differentiated with respect to t. We get ri is differentiated with respect to t, get dou ri dot divided by dou qj. So this term again can be written in the form dou by dou qj of summation I half into mi into vi square. We are differentiating vi square, you will get 2 vi into 2 vi. 2 will get cancelled, and vi is nothing but and then Vi to be differentiated, that is dou Vi by dou Qj. Vi is nothing but Ri dot, dou Ri dot. So again we get the summation I equal to 1 by 2 into Mi Vi square represents total kinetic energy T. So therefore the summation Mi into Ri dot into d by dt of dou Ri by dou Qj equal to dou T by dou Qj. Name this equation as 9. So substituting these equations 8 and 9 in the 7, we get, go back to 7th equation. So the two terms are replaced and delta Qj will come. We get summation I equal to 1 to n pi dot delta Ri equal to summation j equal to 1 to n. So now the equation 10 is, equation 8 is replaced by d by dt of dou T by dou Qj dot minus dou T by dou Qj into delta Qj. Name this equation as 10. So now we have found out the values of summation I equal to 1 to n pi dot delta Ri. So now substitute the values of 6 and 10 in equation 1. We get, here I have written the equation 1, summation I equal to 1 to n Fi minus pi dot into delta Ri equal to 0. So we have splitted the term summation I equal to 1 Fi into delta Ri minus summation I equal to 1 to n pi dot delta Ri. So we have substituted the values of from equations 6 and 10, the values are substituted here. So from equation 6, we get the value of summation I equal to 1 to n Fi delta Ri is summation I equal to 1 to n Qj delta Qj, and here the value of from the equation 10 we get summation I equal to 1 to n pi dot delta Ri is summation j equal to 1 to small n d by dt of dou T by dou Qj dot minus dou T by dou Qj. The common term delta Qj we have taken outside. So finally we get summation j equal to n Qj minus d by dt of dou T by dou Qj dot, you multiply the term inside minus, minus will get plus dou T by dou Qj into delta Qj. So we have taken minus sign from all the terms. You get summation j equal to 1 to n d by dt of dou T by dou Qj dot minus dou T by dou Qj minus Qj into delta Qj equal to 0. Name this equation as 11. Here the delta Q's are independent. So therefore each of the coefficient must be vanished separately. So the coefficient of delta Qj here is d by dt of dou T by dou Qj dot minus dou T by dou Qj minus capital Qj must be equal to 0. This is true for all the coordinates j equal to 1 to 3 up to n. Suppose the external forces are conservative, we get a capital Fi is equal to external force Fi equal to minus delta I into capital V, where V is a function of R1 vector, R2 etc. Rn. So from this we can find the value of delta IV equal to dou Vi by dou Ri. So we know that capital Qj equal to the generalized force capital Qj equal to summation I Fi into dou Ri by dou Qj. So we replace Fi by minus delta IV and dou Ri by dou Qj. You take a minus sign outside, summation I dou V by dou Ri. Delta IV is dou V by dou Ri. So replace by delta IV by dou V by dou Ri, and we get dou V by dou Ri into dou Ri by dou Qj. This is the value of summation Qj is equal to. So hence we get Qj is equal to, this is nothing but dou V by dou Qj. So name this equation as so substituting the value of 13 and 13 in. So the reason we have given here, but V equal to V of R1, R2, R3 and dV equal to dou V by dou Ri into dRi. So dV value we have found out here, and substitute the value of 13 in 12, we get, so Qj value is minus dou V by dou Qj. So the Qj is replaced by dou V by dou Qj there. So we get d by dt of dou t by dou qj dot minus dou t by dou qj plus dou v by dou qj equal to 0. This is true for j equal to 1, 2, 3 up to n. So therefore, if the potential V is a function of position only, then dou V by dou Q dot equal to 0. So therefore, we can add the term dou V by dou Q dot in the above equation 15. We get d by dt of dou T by dou Q, dou by dou Qj dot of T minus V minus dou by dou Qj of T minus V equal to 0 for j equal to 1, 2, 3 up to n. Name this equation as 16. So now introduce a new function L defined by L of q dot t equal to t of q dot t minus v of q. So name this equation as 17, where q stands for q1, q2, q3, qn, and q dot stands for the generalized velocities q1 dot, q2 dot, qn dot. The function is called the Lagrangian function of the system. So therefore equation 17 becomes, so now t minus v is replaced by L. So we get d by dt of dou by dou qj dot dou L by dou qj dot minus dou L by dou qj equal to 0 for j equal to 1, 2, 3 up to n. We are substituting the value of 17 in 16. So we get these n equations, one for each generalized coordinates are called the Lagrange's equation. For giving j equal to 1, you get one equation. For n generalized coordinates, we get for each coordinate we will get one Lagrangian equation. For n generalized coordinate, we get n Lagrange's equation. So thus we have derived the Lagrange's equation of motion for non-holonomic constraints. So thank you, students.